Alright, on this adventure in algebra, we're going to continue studying cosets. And one thing you may have noticed from studying cosets previously, like say, suppose G is the dihedral group, and say H is the subgroup generated by the square of the reflection, then you might notice that RH has the same number of elements as H. And so a question you might have is this true in general? This seemed to be true for all the examples we've ever worked with. Does this continue to be true for every group? And that's what we're going to study in this video. Spoiler alert, the answer is yes. Alright, so here's a fact. Given a subgroup H and given an element G, there is a bijection between the subgroup H and the coset. In other words, given two parallel lines, there is some sort of bijection between the two lines, so to speak. A nice corollary of this is that if your group H is finite, then the number of elements in H is equal to the number of elements in the coset, which is something you may have observed if you've been noticing all the examples we've been doing, that the number of elements in the cosets tends to be the same. Knowing this fact actually will help you double-check your work. If you suddenly have a coset with more elements than what's in the subgroup, then you've made a mistake. So, this is a true theorem. How do you prove it? Well, if you do the way we're used to doing mathematics, you think, well, first I need to define a function, then I need to show that it's surjective, and then I need to show that it's injective, or vice versa. So that's one of the proof approaches that we're used to thinking, is that you define the function, then you show it's surjective, and then you show it's injective, or vice versa. This order generally isn't as important, just that both steps are there. That's not the only way, and that's actually not the approach I'm going to take this time. Remember, we have theorems, so you can always use them. Another theorem we have that we cover in the proof writing course is that a function is a bijection if and only if it has an inverse. So another approach is to define two functions and then to check that they are the inverses of each other. So this one goes from GH to GH, that is the identity function on GH. And that tau composed with sigma is the identity function on H. Turns out, of course, there's always a way to translate a proof using this method to a proof using this method and vice versa, but sometimes it turns out to be much more natural and give you a much shorter proof to use this approach. And that's what I'm going to do. I should say it usually goes without saying that your first time making an attempt like this, I would expect one to try method 1. It's only when rewriting that you might decide that it would have made more sense to try method 2. So here we go. Sigma from H to GH. What's H? It's a subgroup. It consists of elements of the form H. What do elements in the coset look like? They look like things that factor as G times an element in H. What could the function look like? The only obvious thing that would make sense is to send H to G times H. So you're sending an element in the subgroup to something that looks like G times an element in the subgroup. Congratulations, we're very smart. What would be an obvious choice of inverse? Well, what would be the way to undo multiplication on the left by G? Obviously, it should be multiplication on the left by G inverse. That's like earlier in the semester when you had to prove one of these cancellation laws. The trick was to multiply both sides on the left by the inverse. That's the edit undo operation. So let's define tau of G from G, this coset, to H by taking X and multiplying on the left by G inverse. There's one obvious question that I need to check. Is this really the right codomain for this function? Given an element in this coset, if I multiply it on the left by G inverse, do I really get an element in H? Well, let's do the sanity check. If X is in the coset, then X factors G times H for some H in the subgroup. Then tau multiplies on the left by G inverse. By associativity, I can move the parentheses over. G inverse times G cancels, and I end up with an element in H. So congratulations, my codomain is correct. So I do in fact have functions from H to the coset, and from the coset back to H. And as you can guess, since one's multiplying on the left by G and the other one's multiplying on the left by G inverse, and multiplication of an element by its inverse is the identity, you can guess what's probably going to happen when I compose. Right? You might expect composition one direction is going to give me GH times G inverse, and composition the other direction ought to give me G inverse times G. So let's check it. We want to prove that this tau is actually the inverse of sigma G. Let's do the composition. Tau of G takes X and multiplies on the left by G inverse. Sigma G takes whatever and multiplies on the left by G. So by associativity, I move the parentheses over. G times G inverse is the identity. The identity times anything is X. I chose an arbitrary element in the coset. I did this calculation. I got that element back. Congratulations. We have a winner. Sigma G composed with tau of G is in fact the identity function on the coset. Similarly, if I do the composition the other way, I'm multiplying by G and then by G inverse. Same calculations, I just get H back. This really is the identity function on H. So these two functions are inverses of each other, and so by that theorem from the proof writing course that I've already covered when we discussed the symmetric group, a function is a bijection if and only if it's invertible. We found the inverse of sigma, ergo sigma is a bijection. Note this subscript is only here because it depends on which coset you're talking about. I should clarify what I mean there, and I will by going back to linear algebra. If I'm taking a line here, and I'm taking a parallel line, the point is that somehow you should be able to translate from one to the other, and the definition of the translation depends on where you're going to send the origin. Once you define that, you've got a bijection. That's basically what this function does. But as you can tell, the choice of bijection depends on the choice of element from the coset, or from the parallel line. And so there's actually more than one bijection. There's a different bijection for each element in the coset.